Okay, so here what we're going to do is go over something called the 2-point measurement protocol. And what this is going to do is it's going to allow us to build probability distributions for physical quantities that don't have a Hermitian observable associated with them. So two examples of these are heat and work, which is what we're interested in. And these don't have some operator that we can measure to get some expectation value of that operator through something that would look like this, where ρ is going to be the state of our system and O is this Hermitian operator. So O is going to equal dagger. So like we just said, there's no Hermitian observable associated with heat or work, so these things don't exist. So what we need to do instead is find a way of defining these physical quantities in terms of operators that do exist, and that's what we're going to do now. So the goal of what we're doing with this 2-point measurement protocol is going to be to build probability distributions for these physical quantities, like we said, heat and work, which don't have Hermitian observables associated with them and therefore cannot be measured directly. And we will see shortly why they're probability distributions. So we can imagine the probability distribution might just look something like this. And let's think about what we're actually, the physical system that we're thinking about. So in open quantum systems, we're interested in some small quantum system, like a qubit or something like that. And we say that it's in contact with some environment. So we have our system here, it's surrounded by the environment, everything else inside this box. And then we make this assumption that this entire thing is a closed quantum system. And what we are interested in is the amount of heat and work that gets exchanged or gets done on or done by the system and the environment together. So we've just said that our system is in contact with its environment, and let's think about the Hamiltonian that describes this entire system. So the total system is going to be made up of the system part, the environment part, and their interaction. So we can imagine something going on at the boundary between the system and the environment here. And this will help us think about why the heat and the work are going to be described by probability distributions. So when we're thinking about an open quantum system, we're usually thinking about something very small. So let's, for example, think about a qubit, which isn't necessarily small, but let's think about one that is, like a trapped ion or something like that. So if our qubit is very small and it's surrounded by a large environment, then the interaction, which is going to be proportional to the surface area of the qubit, is going to be of a comparable size to the system Hamiltonian itself, which is going to be proportional to its volume. So as the system gets smaller and smaller and smaller, the surface area to volume ratio goes up, and therefore this interaction here is going to be comparable to the system Hamiltonian here. And what this is going to mean is that small fluctuations in heat, which in classical thermodynamics we can ignore, are going to be comparable to the energies that we're looking at. So in open quantum systems, what we're always trying to do is figure out what's going on with the system. That's the thing that we care about. The environment is going to be too big and it's going to have too many degrees of freedom for us to simulate what's going on with that. So what we do is we derive these things called master equations, which tell us how the dynamics of the system evolve in time, which has two main contributions, which is the unitary internal dynamics of the system due to its Hamiltonian, and then on top of that, small, not always small, but correction terms, which come from the interaction Hamiltonian. So if the system was by itself, like this, then the state of the system would evolve according to the Schrödinger equation, and the dynamics would be unitary. But when we have the system surrounded by the environment, the dynamics of the system state are now governed by what we call a master equation. And this master equation takes into account the environment's influence on the system without having to track the state of the environment, which we cannot do. So this is an important point to think about. We're always trying to figure out what's happening with the system, even though the environment is coming in and it's messing things up, but we cannot describe the state of the system, the state of the environment in any great detail because it's too big. And what we're trying to do is simulate things numerically, and the state space just grows way too big for us to do anything. So all we care about is what's happening to the system, and that has two parts: the system by itself and then the influence of the environment on the system. So like we just said, we've got our total Hamiltonian, which is going to be broken down into a system part, an environment part, and an interaction term. And at this point, what we're going to do is we're going to make a big, unrealistic assumption. But don't worry, what we'll see later on is that this assumption helps us derive something which is a feasible thing to do. So that might not make sense right now, but we'll see soon. So what we're going to do is assume that we can make projective measurements on the bath. So like we said, that's not actually going to be possible, because in order for us to, example, measure the bath Hamiltonian, environment Hamiltonian, same thing basically, we would need to know the state of the environment. And this thing is usually not going to be possible. However, like I said, we'll see soon that this isn't going to be an issue. So the 2-point measurement protocol, the clue is in the name about what's going to happen. And essentially what we're going to do is we're going to measure the environment Hamiltonian twice at 2 different times. And so let's think at t=0, we're going to measure this environment Hamiltonian. And let's say that the outcome that we get is h0. It's going to be one of the eigenvalues of the bath Hamiltonian. And then time tau later, we're going to measure the Hamiltonian again, and let's say that we get h sub tau. So these are both going to be eigenvalues of the bath Hamiltonian. And now what we're going to do is define a stochastic quantity. We'll call it delta h sub tau. And that's simply going to be the difference between these two values. So we've taken our two measurements and we've defined a value that is the difference between the outcomes that we got. And like we said, both of these are going to be eigenvalues of the bath Hamiltonian. So let's repeat this a bunch of times. And what we can then do is build a probability distribution at a specific value of time. And it's going to look like the sum over all possible values of h0, so the initial measurement outcome, and h tau, the second measurement outcome. And it's going to look like the probability of getting h0 for the first measurement multiplied by the probability of getting h tau for the second measurement, given the fact that we got h0 for the first measurement. And then it's going to be multiplied by a delta function, which is centered at delta h tau. So the way I think about this is, imagine we've got this probability distribution. It looks something like this. And we just got a bunch of delta functions where the height is given by this product here, and the position along the x-axis is given by delta h tau. And then eventually our probability distribution is going to look something like this. Okay, so we've now got our definition of the probability distribution for delta h at time t, where delta h is going to be what we define as the amount of heat exchanged between the system and the environment. And we said this was a sum of all possible outcomes of the first and the second measurements in the two-time measurement protocol of the probability of getting h0 for the first measurement and the probability of getting h tau given that we got h0 multiplied by this delta function centered at delta h sub tau, where delta h sub tau is simply the difference between the two measurement outcomes, h tau and h0. So this is what we want. We want this probability distribution. But we can't get it. So instead what we need to do is redefine this probability distribution in terms of something that we can get, that we can then transform in a nice way to get the probability distribution that we do want. And we can do this using the Fourier transform. So we define a characteristic function, which is going to be phi of chi at time tau, as the Fourier transform of this probability distribution. And what we will see is that we are able to find this characteristic function, which we can then simply inverse Fourier transform to get the probability distribution that we want. So what does this characteristic function look like? We're going to integrate over all of these delta h's, and well, then it's just going to be the normal definition of the Fourier transform. Okay, so this is a characteristic function, and this is going to be the main object of focus from now on. So while we want the end product, we do want the end product to be the probability distribution, but we can't get the probability distribution from, how do we say, we can't get what we need to get the probability distribution, but we can get the things that we need in order to build up this characteristic function, and then we can Fourier transform it and get what we want, which is the probability distribution. So that might not make sense, but hopefully it will soon. So here we've got our characteristic function, and let's quickly figure out what it's going to look like. So what is this probability? Well, we had it on the slide before. Just bear with. So it's this sum over all the h0, h tau, ph0, ph tau given h0, and the delta function. And we've got this integral over delta h with a delta function and a delta h up here. So we just evaluate the function at delta h tau. So we've still got the sum, we've still got the probabilities, and now we have e to the I chi delta h tau. And let's remember what delta h tau is. It is h tau minus h0. Okay. So now let's think a little bit about what these probabilities actually look like. So how do we find out what ph0 is? So what is this? We measure the Bath Hamiltonian and we get outcome h0. So what's the probability associated with that? Well, what we're going to do is take the trace of what we'll call rho naught, which is just going to be the initial state of the system and the environment. So at time t equals 0, the state of this entire thing here is going to be rho 0. And to get the probability of getting H naught, we simply just take the trace of rho naught with the projector onto H naught. So let's think about what this is. We have HE, and if we write this in its spectral form, it's going to be sum over all of the H's, where the H's are the eigenvalues, eigenvalue, eigenvectors. So when we measure this Hamiltonian here, we get one of these outcomes, and then our state gets projected into this associated eigenvector. Okay, nice. So we've got pH naught. Now let's think about what the other probability that we need is, which is pH tau given H naught. But before we do that, we're going to need to think about what happens to the state of the system after we do the first measurement and we get outcome H naught. So let's put this aside for a second. So after we measure the environment Hamiltonian and we get outcome H naught, what happens to the state of the system? Well, we go from rho 0 to the projected state. And it needs to be normalized, so we divide it by this probability here. So let's just write this out explicitly. We've got H naught, rho naught, H naught, divided by the trace of rho naught with H naught. Okay, so this is our state. It looks complicated, but it'll simplify down soon, so don't worry. And what happens next? Well, we're going to do our second measurement at time tau. So the state is going to evolve. This state here is going to evolve. How? It's going to evolve unitarily because it is the state of the entire system plus environment, which is a closed system. So rho naught after the first measurement goes to this big complicated projected state. It's not complicated, it just looks a little bit messy. So we performed our first measurement and now we wait a time tau, and then we're going to perform our second measurement. So we need to figure out what the state is after time tau. And it's simply just going to be, let's just put a unitary here and put the dagger here. And what is this unitary? Well, since the entire system is closed, it's simply the exponentiated Hamiltonian with time. Nice. So this is the state of the system when we perform the second measurement. So now we're ready to think about what this probability is going to look like. So it's just going to be the trace of the state of the system with the projector onto the outcome H tau. So it's going to be this horrible state divided, this is for normalization, times the projector onto H tau. Okay. And what we're actually interested in is the product of the two, right? pH naught, pH tau given H naught. What was pH naught? It was trace rho naught, H naught with H naught. And pH tau given H naught is just given here, so I'll just quickly write it out again. Actually, now I won't write it out again, but what we'll see, look, this trace rho H naught is going to cancel out with this one here. And so the end product is going to look like this. So we've got the unitary, projector, rho naught, projector, unitary, and then projector onto H tau. Okay, so let's look at this in a little bit more detail. So let's now input the probability that we just got into the characteristic function. So we need the sum over all of these, and then the two probabilities, and the exponential. Okay, so the two probabilities we found on the last slide is going to be trace u of t, h naught, rho naught, h naught, u dagger of t, h tau, e to the I chi h tau minus h naught. Okay, so this looks complicated as anything, right? So let's try and simplify things. So these are all operators here, and this here is a complex number. So this we can put anywhere. So let's break it up into e to the I chi h tau and e to the minus I chi h naught. And then let's rewrite our characteristic function in a different way. So we've got u of t, and then I'm going to put the e to the minus I chi h naught here. And then notice that all these other objects need to stay in the same order because they don't necessarily commute. And I will put the other part of the exponential here. Why have I done this? Well, it's because e to the I chi hb acting on one of these eigenstates is simply going to be e to the I chi, and instead of hb we just write the eigenvalue times the eigenstate. So what that means is that I can rewrite e to the I chi h naught as e to the minus I chi h naught as e to the minus I chi hb times h naught. And similarly with e to the I chi h of tau times h of tau, I rewrite this as e to the I chi hb h tau. So that's what I'm going to do right here and right here. Great, so now I can rewrite my characteristic function with the Bath Hamiltonian in the exponential instead of the eigenvalues. So what's this going to look like? So we've still got these two sums. We're going to have trace, time evolution, e to the minus I chi, and now we've got the Bath Hamiltonian. Okay, so I think I've been confusing in that I've been calling the bath and the environment the same thing. So when I say bath, I mean environment and vice versa. And then we've still got these projectors. We've still got the initial state, and we've still got the projectors again. And then we have the other part of the unitary dynamics. And then we have the exponential with the Bath Hamiltonian again, except now we've got a positive sign. And again, we have the projector onto the final outcome, final measurement outcome state. Okay, so now I'm going to neaten things up slightly. I'm going to define the sum over h naught of this thing as simply rho 0 bar. And then I'm going to use the fact that the sum over h tau of h tau equals the identity. Why is this true? Well, it's only true if we perform enough repeats of this 2-point measurement protocol. So let's think what happens. when we perform the first measurement, we get one of the eigenvalues of the Bath Hamiltonian randomly, and similarly when we perform the second measurement. So if we perform this a bunch of times, eventually the sum over h tau of the projector onto the h tau state is going to have every possible eigenstate of the Bath Hamiltonian. So all eigenstates of the Bath Hamiltonian will be included in here, and the sum of all projectors onto eigenstates of a Hermitian observable equals the identity. And what's that's going to do is that's going to allow us to rewrite the characteristic function in a very nice form, which will be, okay, and I'm also going to use the cyclic property of the trace, which is that the trace of AB, where A and B are operators, equals the trace of BA. And then we will get a nice expression for the characteristic function, which will be e to the I chi hb times u of t times e to the minus I chi hb times rho naught bar times u dagger of t. And this is the thing that we are interested in the most.